Hello, I'm Sophia, and this is the first paper I'm analysing for the current Complex 529 assignment. This one's authored by Ramal Hakimzadeh, and I believe that's how you pronounce his last name, and Jim Dowling. They're talking about a new method for describing cloud operations. So a cloud operation refers to some process which operates or runs cloud infrastructure and its environment. Horizontal scaling is sort of an obvious example of a cloud operation, and when we consider what's involved in horizontal scaling, we realize that it's not an atomic operation. There are a number of different steps involved in actually performing that operation. You need to spin up nodes, run software, there might be some networking to configure, you've got to link to services like a database or a microservice registration system. And so the problem is that these cloud operations themselves, how do you do auto-scaling as an example, has received a lot of research attention, but the management of the configuration required in order to run those cloud operations in the first place hasn't received as much attention. And so in a lot of cases, we end up in a situation where this configuration ends up getting managed on a day-to-day basis by humans. And this approach doesn't really scale well, it's error-prone, there are some problems. So this paper explores two different, closely related research questions. The first is it possible for us to increase the agility of programming these cluster-specific cloud operations? And the second one is, can we improve the automation of elasticity? And so here I've got a diagram from Microsoft demonstrating the difference between an application using a more traditional monolithic architecture and an application which is composed of microservices. And you can see visually here that the microservices approach has a lot more moving parts. There's a ton of extra configuration to handle, and we can probably sort of imagine how this gets quite difficult to manage by hand using manual one-off scripts. So how do we go about managing this complexity? Well, no one knows. It's an active area of research. Spotify recently released a system called Backstage, for instance, which is a toolkit for producing developer portals and managing some of these configuration aspects which we're discussing. And that's very recent. It came out only a couple months ago. And in my personal life, I've also interviewed at Foodstuffs recently for a cloud architect role. And one of the things they brought up was that their story around configuring their microservices is not very well designed. There are 15 different configuration files that need to be tweaked by hand, lack of standards around everything, and they really want to clean that up. So it's a huge problem, and no one has a particularly great answer. So we've got a few different approaches out there for modeling and orchestrating cloud operations. We've got ones which are based on the topology of the system or the desired state of the system, and so I've listed a few different systems which are in my citations document. I've put these together under one bullet point because they suffer from similar drawbacks, which we'll go into later. And then you've also got a service-oriented architecture approach to orchestration. So Disnix is a configuration manager built upon a package manager for Linux called Nix. And this is actually quite similar to the system that we're going to be investigating today. It's based on this sort of functional style of expressing your configuration. Another way you could do this is something like with a Docker compose file or a Kubernetes cluster configuration where you break your application down into disparate services and worry about the configuration for those services. And then of course we've got manual orchestration approaches where a systems administrator will write a script using something like Puppet or Chef in order to manage these cloud operations. And so a little bit of context before we get into describing the system being discussed here is a concept of something called higher order functions. So on the left here I have an implementation of a function which calculates the nth Fibonacci number. And something that's sort of interesting to note about this is that firstly, it's very expensive to compute large Fibonacci numbers. It's an ON squared algorithm. And the second thing is that if we have the n-1th Fibonacci number, we actually theoretically shouldn't need to do any work in order to calculate the n-2th Fibonacci number, because the n-1 number is produced from the n-2 number. But this naive approach doesn't really support that. And so it would be nice if we could sort of cache this result. And so one way we could do that is by hard coding it into the Fibonacci function, but that's not great because we can think of other applications where this caching might be useful. So on the right here we have a function called memoize, and what's special about this is it takes in a function as a parameter and then returns a brand new function. And it adds that caching functionality to the function we passed in a reusable and composable way. And so we call memoize a higher order function because it's operating on functions as opposed to regular values. This is a very important concept to understand when we're talking about this new approach, which is called upscale. And in upscale, cloud operations are modeled as a series of higher order functions. And these higher order functions take in other operations as dependencies, those are the function parameters we're talking about, and they produce two new functions, a key function which acts as a planner, and a value function which acts as an actuator. And then in addition to this sort of graph of functions, we've got something called the operation controller. And the operation controller walks through the graph of our functions and produces a final plan. And then after that, the operation controller sort of navigates this graph, this plan, and executes it in order to run all of the cloud operations which need to be ran. And so this is pretty interesting. The advantage of this approach compared to something based on topology or desired state is that the topology and the desired state of the function are implicit results of our value functions. We don't actually need to explicitly model this stuff up front. It's a natural consequence of running our functions. Compared to the service-oriented architecture approach, we actually get far more granular configuration because if you think about a Docker file, all of the configuration is sort of bundled into one block for each service. And things like setting up a load balancer in a web server, you have bidirectional dependencies where the web server needs to be in a certain state before you can set up the load balancer, and then once you have the load balancer, you can continue working on the web server. And so by breaking everything down into separate functions, we can actually model those dependencies really easily. And obviously compared to manual orchestration, there's less human involvement and it's more reusable. So in order to measure the effectiveness of this approach, there are two evaluation methods being used. The first is to look at the programming effort of modeling these cloud operations. So here we have some code written in Apache Brooklyn, which is another related project. And on the right we have the same operation modeled using this new approach, and you can sort of see that we're passing functions in. We're also doing things with partial application, which is another functional programming concept. And you can see that this code is shorter, and it's also more expressive depending on, well, it's more expressive for some people anyway. And the second thing is to take a look at the order of growth plots for a system running under this new way of modeling cloud operations. So this project is actually an open source project called Caramel, and it's built on top of Chef, which is one of those manual orchestration approaches, and we can sort of see how the system scales in terms of number of functions and state items as we increase the number of instances. We get nice linear scaling here and some sort of polynomial scaling with respect to dependencies. So in terms of critique, it's a bit of a mixed bag for me. I'm not totally sure I like the evaluation of programmer agility. I think there's a lot more that goes into it than just the number of lines of code you're writing. There are things like readability and productivity that we need to sort of think about, and so I'm just not really totally sure about that. The second thing is that the authors make a lot of note about how in, say, something like a Docker file, you need to give an explicit name to the various services in your file. And supposedly this is a problem because when you're manually assigning names, it doesn't scale as well. But it doesn't really make a whole lot of sense to me, and I'm sort of wondering if I'm missing something very obvious, because in this approach, we still need to give names to everything. It's just that we're naming functions. And just because you give a name to, say, a MongoDB service in your Docker file doesn't mean that you're limited to just one MongoDB instance. You can still scale it up. And the other thing is that there's a lack of sort of analysis around the effectiveness of the system. There aren't any sort of formal guarantees that I can see. And the last thing is that I don't actually know if the project even exists. So you can go to the Caramel Chef GitHub page, but it doesn't seem to implement the system that they're talking about here. I can't see any sort of functional programming stuff. It's all YAML files, as you'd expect from sort of Kubernetes or Terraform or something like that. So it's a bit of an odd one. I like the idea, but I don't think the implementation is there, and there are some sort of question marks over certain aspects of the system.